In this video, I'm going to get into operating system pieces, I guess. In a previous video, I introduced that I'd probably get into building some type of operating system for my 65265 here. And I don't have a real detailed roadmap to get that done, but I'm going to kind of work through it piece by piece. And this video is maybe the first of a series of, I'll just call them rambling operating system videos on things I'm thinking about, things I'm doing. And specifically in this video, I thought I would quickly introduce, what's in my mind as far as what I want for an operating system functionality. What are the basics? And keep in mind, this is going to be really basic. So if you're thinking about a full-fledged operating system like DOS or something like that, I'm not going to get to that point. But, how far can I get is a question. I've done some early power on self-test routines to test some of the hardware that I have not used up to this point. I'll talk through that in this video. And then I've started to lay out a framework for how might I have routines in the operating system that an application can call. So as I get to the point that the OS is working, I want to be able to quickly build applications to run on the OS, and I want those apps to be able to use the abstracted hardware that the operating system is providing. And so that's what I'm going to get into in this video here. So first things first, what are the basics of an operating system, I guess, that I'm going off of? So three things here: resource management, hardware abstraction, and program execution environment are probably at the top of my list. So, managing the CPU itself, I/O devices, storage, abstracting all of that into some type of hardware abstraction that applications can use with little effort, where I can just call a command to draw a circle, and my application doesn't have to know how the circle is getting drawn. It just is handled through the abstraction and the resource management of the operating system. And then for me to run applications, I need some type of program execution environment. So how do I go from the OS and actually launch an application, have the application have, reasonably easy access to operating system functionality, system type calls? How am I going to manage memory? Can I eventually get to the point of multitasking? That's a stretch goal for me, but I would love to get to that point somewhere down the road. So those are the three basics that I'm moving forward with, and I'm sure I could break that down in a lot more detail. I do have a blog post started on this operating system work, and so I'll capture some of my thoughts as I go there. And of course, as I'm going through this, if you've got ideas, definitely drop me a line, or you see me doing something that there's a much better way to do it, do let me know. I know as I approach this, some of the things I'm going to do are probably the simpler side of things, knowing that there's a better long-term solution at some point that I'll get to. Like even what I'm going to get into today, I'll talk about jump tables for getting to operating system routines from an application. I know there's a different way to do that. I think there's many ways to do that, but I'm taking one approach in this video to start to get me going, and maybe down the road I'll come back and really rethink that and maybe refactor that. I would maybe flip over to this slide here and just mention my address space real quickly. So I think I've got this correct here on this graphic. The 65265 is a 24-bit address space that you have. So that's 16 megabytes going from 0 all the way up to FF. So that's the range that I get to play in. Now, the way I've set up, this board that you see here is that I have, the RAM. I have external RAM, so I come over here and there's a little RAM chip right here, and that RAM chip is really giving me 32K of RAM minus any of the space that's used by the 265 for I/O registers or other types of things. Then I have a 32K ROM, that is this ROM here, and that is really my primary ROM. So it's an external flash, and that is serving as my primary ROM. Extended RAM, I have another IC over here that is an extended RAM, and you'll notice that's kind of an odd size. It says 448K. It's actually 512. However, the first 0000 through FFFF is kind of subtracted from it. It's not available because those addresses and the address decoding are used by the ROM and RAM that you see below it. So really I've got 448K of usable address space there. I'm sure I could find a different way to do that, but that is using the chip selects built into the 265, and I think that's maybe how it's intended to work here. If not, maybe I can adjust that later. Then there's a big gap in address space that I'm not using, so there's a bunch of stuff I could fill in there later. But then I have a secondary ROM, and that secondary ROM is this IC right here, the second ZIF socket, and that is a 512K ROM or external flash that I can use, and that goes from bank 40 up to 47. And then there's another gap of addresses that I'm not decoding or doing anything with, and I get into this C0 all the way up to FF banks. And in those, I'm not using that space very effectively. I did what was quick and convenient, knowing I don't need all of those addresses. But throughout that space, I have I/O devices like some of my versatile interface adapters. And then I also have a 2K dual port static RAM up here that's used between this processor and the secondary processor on another board if I get that running at some point. And as far as the vias are concerned, I've got, a couple vias, a few vias on here. Actually, there's one underneath this screen, there's one underneath this screen, and there's one over here. So there's 3 vias that I'm controlling within that address space. And the way I've set it up is I have a decode chip that I could add additional I/O within this C0 to FF bank space for future expansion if I need to do so. So that's the addressing I'm working with, and like I mentioned, I have static RAM, both the initial 32K plus this, I'm calling it extended static RAM. I have my primary flash, I have a secondary flash, I'm just calling that ROM and secondary ROM, and then I have I/O and some dual port static RAM. Now, up to this video, I had not previously really gotten in and tested, did my secondary static RAM here, this extended static RAM, did it, get soldered on correctly? Is it working as expected? Was the design correct in my schematic? Same thing for the secondary ROM, same thing for this dual port static RAM over here. So those were questions. I had not been using them up to this point. So I did implement power on self tests for those 3. So when I power on the system now, I do run out to this secondary extended static RAM, and I test the entire set of memory there that is accessible, that 1000 all the way up to, the 10000 all the way up to the 7FFFF. I test that. I then also test access to the secondary ROM. I read the very beginning of it. I read the very end of it, looking for a certain signature. And if that's not found, then I show a failure. And then I also test writing to the 2K. I fill the 2K and read the 2K back a couple of different ways just to validate that that's all working. And maybe I can switch over and show you that power on self-test functionality here real quickly. I will have this code posted, of course, like I usually do with these videos, but I made a separate assembly file just for post. And basically, when I turn on my system, it calls the run post tests. And in the run post tests, I'm going to go out and run a few different tests. So I've got an extended static RAM test that I run. I then also have another test down here, which is to test the dual port static RAM. And then I also test the secondary flash. And just real at a cursory level, if I go to, let's just say, the extended RAM, I'm going to come in here and really just run through all of it. And I want to write out AA. That's a test pattern that I write out. And then when I get done with that, I want to verify all that. Then I write out 5.5 and I verify that. And so basically, I'm going to just loop through, writing all of the 5.5s and then verifying all the 5.5s within a specific bank. And then I'll increment the bank as I get down through this, and we'll continue basically going back through that. So that is what this routine is doing. And you'll see that there's a test bank here, and that's what I'm kind of iterating through, and then eventually would increment that down here, flip to the next bank. And so if I go back to my address space and look at this static RAM, I have an address bank of 1, 2, 3, 4, 5, 6, 7. So those are the 7 that I need to run through, and in each of those, do the run through the 64K within that bank. And that's essentially what this test is doing. And it's doing both AA and 5.5, which I think is a pretty common way to just make sure that you don't have stuck bits or bits that aren't working, whatever. So that's the test that I do on the extended RAM. And you'll see that I'll power on my system here, so you can see that on the screen. I do the same thing with the dual static RAM. And then, no different really here. So simpler routine, because I really only have one bank I need to worry about. I don't have to flip through a bunch of banks, but I can just say, here's my bank, go do the AA, do the 5.5 testing. Maybe a quick note back on the extended static RAM, because that does take a little bit longer. As it does each bank, I write out to the screen which bank it's testing. So you'll see that when the power on self-test runs, is I write a 1, a 2, a 3, just so I can see that the status is moving along. And then I have the secondary flash, and the secondary flash, basically I'm going to go out to the secondary flash and I'm looking for a specific set of information. So at the very beginning of the flash, I'm looking for REHSD exclamation point. And so if I find that, that tells me that I read the very beginning, the start of the flash. It's the first 6 bytes I expect it to be in the flash. And then if that succeeds, I then also go to the very end and I check for the same string, REHSD exclamation point, at the far end of the ROM. And so that's the last 6 bytes, which would be this 47 FFFA is where that's at. And flipping back over here, that's just at the top of this. So I have a little mark at the beginning of the ROM, at the end of the ROM, however you want to visualize that. And I'm testing for that. Obviously with the ROM, it's probably not a good idea to be trying to write to the ROM to read it back. So it's really just a read test. So those are the tests that I run as part of this run post tests. And when my system turns on, I am going to go ahead and get down, actually scroll up. My system comes up, I get into the start. And in the start, I do a bunch of initialization, but then I eventually get down to this run post tests. And I'm sure I could do them earlier in the startup routine, but that's the point at which I do them. And maybe I'll just zoom into my screen. I'll power on my system real quick just so you can see what the result of that is. So my system comes on and it initializes this screen that I'm using for a lot of the output. And there's the extended static RAM test. And then I show that it passed. There's the dual static RAM test, pass, secondary flash test, pass. Now maybe as a test, I'll power it off and I'm going to remove the secondary flash, which is I'm testing that, I'm looking for those signatures just so you can see what a failure looks like. But this comes up, my first 2 would work and then the third one fails. Now it's kind of hard to simulate a failure on those static RAMs, but this should give you the idea that if it fails, I'll get an indicator like this that says fail. So that'll give me a little bit of confidence that this hardware, these ICs here are working and access to my flash ROM seems to be working as I go through those tests. So then I continue on and I say, okay, I've got static RAM and ROM, both my primary, my secondary. I have this additional dual port static RAM for my PIB when I interconnect 2 of these microcontrollers at some point. I'm pretty confident that hardware is working fine. So then I want to start thinking about this whole operating system applications thing. And the way I'm going to start approaching this is I'm going to use this initial 64K RAM and ROM combination for my quote unquote operating system. And then for now, I'm going to say that the secondary ROM, I'm just going to reserve for applications. And that's 512K, so I can put quite a bit in there as far as ROM data and application data or applications. And then I've got this entire 448K of extended RAM that the operating system is not using, does not really even need at this point, but I can make that available to the applications so they can load up and do their work within that space, minus any zero page type of work that they need to do. So then I've got to think about, how am I going to load up an application? How is it going to work? And I'll visualize that with these two boxes here. Maybe on the left is my OS. That again is in that first 64K. The applications are in later address spaces. That really the secondary flash is really where those will be at. And I want to be able to, in the operating system, have all the hardware routines. So whether that is writing to this LCD you see right here, or it's writing to this LCD, or it's accessing the real-time clock or SD card or any of the other functionality I might have, all those hardware routines should be part of this operating system. And the operating system might have other routines that I want to build in that I know I'm going to reuse. Whether it's formatting or converting something from ASCII to hex or hex to ASCII or whatever it might be, those types of routines that I know are going to be common should probably be in the OS. So it might be that from an application, I want to write out to the UART on this. The application shouldn't need to know how to do that. It should just be able to say, send a serial string and make a call to the OS, and the OS deals with everything underneath it, from converting characters to getting the data out through the UART or receiving it back in. So then I want to build apps, and saying that I'm going to put those on the secondary flash. And really the way I want to think about it is this secondary flash, I almost think like a cartridge. You think about game cartridges with a flash ROM in it. Can I treat this like that? And I know it's a ZIF socket, it's not a cartridge slot, but I think the idea is pretty comparable. Could this be a little game cartridge type of thing where I could go out and I could grab, another one of these ROMs, and this isn't the same one over here, but I could just swap that out, put this one in, and it's a different set of applications that I can load. So I need to make sure that ROM, whatever's on it, can be assembled completely independently. It doesn't have to be assembled with the operating system. I can just go out and build it, do its thing separately, and really treat it like a swappable ROM cartridge is how I'm thinking about it. So I need independence, or a disconnect, and maybe I'll call it loosely coupled. The application isn't having to be built with the OS, but it still should have the ability to leverage functionality of the OS. So the way that I'm going to support this is that, from my operating system, you might go in and, as an example in previous videos, I'll boot this back up. When it comes up, I'm starting to kind of give it an OS feel here, and I can do things like help and see, what can I do in here for functionality. And one of those things might be, I want to get the version, and I get my version back. But one of those might be that I want to just say, I want to run app1. So I type app1. And here in this visualization, what I want to do is basically do a jump to a subroutine over in the secondary ROM. And that application then, let's just say app1, I want to have it then access hardware back on my main board through the operating system. So it might then turn around and make a call back to a jump table. And so this jump table is something I'm going to have to come up with standards on, and basically have a standard way to connect to it, interface with it from my applications. But that just comes down to me figuring out what I want that standard to be, and then creating a document really for myself so I don't forget what that standard was. But then from that jump table, I can get into all the operating system routines and hardware routines. So this will give that app1, access to my OS, to the hardware abstraction functionality. And it doesn't have to, again, be built with the operating system. It's a separate ROM that I'm creating the binary for and writing. And maybe at some point, instead of a ROM, it's a CF card, it's an SD card, it's some other type of storage mechanism, or even uploaded through serial. Now, work I know I have to do for today, what I'm going to show is that I'm just jumping to an address space where I expect the program to be on the external, the secondary flash. Now, in the future, though, I think I can have a mechanism that gives me a listing of what's on the flash. And so that would just be a little table of contents type of thing I would put on the flash that says, okay, on this flash are these 10 programs. If I put a different flash in, that same little table of contents would say, here's these different 20 programs, whatever it might be. So I can do a directory, get the addresses, and then say jump to one. And obviously prompt the user, this is what's on the flash, what do you want to jump to? And make that more dynamic than what you're going to see today. But then the app, to get to the jump table, I have to have this jump table in there. Again, I have to have that standardized and documented, and then make sure all my different apps, use it in a standard way. And for today, I'm going to use assembly, but my expectation is to also try this with a C compiler, and I believe it's pronounced Calypsy. This is the one I'm going to experiment with. So instead of using 265 assembly and this retro assembler that I'm currently using, I want to go out and use a C compiler so I could write some routines in C, and then I can compile those, load them with a JSL, and have them run no different than the assembly type of work that I'm doing. So that'll be a video down the road as I get a chance to experiment with that and see if I have any luck with that. I'll jump over to my code again and just point out that I have an OS, and in this OS routine, well, not routine, but OS assembly file, I have a routine that is execute command. And so when the user's putting an input, at some point they press enter. When they press enter, it jumps over to execute command. Execute command just says, well, which command are you running? Are you running the CLS, a dir, a vir, a help, a hello, or an app1? And what I'm going to do here is I'm going to run app1, and then when I run app1, it's going to jump down to a block of code that says do app1. And that's just going to jump over to, like I mentioned, a hard-coded space in my secondary flash, which is right now at this 40,000 or bank 40 and then 1,000 within that bank. And again, this is hard-coded. I will make that dynamic later, doing some type of a directory or listing of what's on the ROM that I can jump to, and maybe prompt the user to then jump to that. So then I have a completely separate ROM file. Now, first of all, this code, my primary, the OS, all of that is part of this, primary. This is the what leads into everything. And if I do a build here, so on my keyboard, I hit Control-Shift-B to do a build, and that will spin up retro assembler. It builds it down here, and I can see, that all passes. Good to go. I have a separate file, though, that is the secondary, and it has its own bin file. So I'm going to have my first ROM binary file to program, and the secondary has its own. And so this is just a one file solution at the moment, but then I can build it, same thing, and it creates a separate file, and it shows me the size of it. That's my 512K that it's written out. Versus this previous one was a 128K, of which only 32K is used in my address decode. But this is creating a separate ROM. And when I go from my primary and I say that I am in the OS and you've set to do app1, I'm going to jump over to the secondary to this 40,100. Well, you have to remember the physical ROM is only 512K, so the addressing starts at 0, and it doesn't go as high as 40,000, but that's where it's going to show up in my address decode. So physically, this ROM has a certain range like you see here, but to the system, to the 265, this is how it's going to show up, the way that this chip selects 6 and where I have it positioned. And that gives me access to that secondary ROM. So I'm saying to jump to 40,100. And so that really is anything in here that I say at org 1000, that is 1000 plus the 40 offset gives me this address. So this app1 is what it's going to jump to. And so when I say to jump to a subroutine long, and I specify that, it is jumping over here. And right away, the first thing I do is I do an app init. And what I'm doing inside of app init is I'm just setting up a pointer. And I'm setting up a pointer to a very specific address in my operating system. And that address is F200. And so I have a variable place to store a pointer. I want to point to this location of F200. And this is just filling in that pointer to say, I want you to go to that location. And that location, if I get over to my primary and I scroll down to that, looks like this. What I've done at F1000 is I put in an OS version, a major, minor, and a build number, so I can kind of have that embedded into my OS ROM. But then I set up a system call table, and this is going to be a series of supported routines that an app can call into the OS and make a call to one of these. And then I have a call OS routine. So from my ROM, I'm making a pointer to this call OS so that later I can jump to that OS call. It's going to come into this, and then from here I can use this lookup table to say, well, which specific OS system call are you trying to make? And I've only set up one, so not too exciting yet, but this will get filled in with dozens or hundreds of different calls I can make. And the first one I did do, just for simplicity, is a print char. And ILI is this, TFT screen here. The interface is an ILI chip, so I just preface everything with this ILI. So I have a call table. I support one system call currently. This is the entry from the app into my OS to make that call. So then I come over here, and what am I doing? I say I want to load up this specific X value. And so basically I'll have a listing of values for which supported OS calls do I have. Right now there's just one. I can do a print char. It's a value of 0. So I say load up a 0. I want to do a print char. And then it takes a parameter. I need to send it what character. I want to tell it a T, capital T, and then I'm going to jump to that. Then I'm going to load up an E and jump to it, S, jump to it, T, jump to it. So from my secondary flash, this application's running and it's making calls back to the OS, sending in some parameter data, the TEST, and making a call to print to my TFT screen. There's a little bit extra to this besides that. You'll notice this was called app init, and this is calling this OS, JSR. And there's probably a better way to do this, and it has to do with I'm trying to jump to an address that needs to be a long address, but both assemblers, I've not been able to figure out how to do that with a label. So I want to put a label here, like just say, don't jump to 47FFE0. Instead, I want to say jump to, and have some nice friendly name to that. But this is how I got it to work. So I have this routine that, first of all, this is a JSR, and then I do because that's a jump subroutine. It doesn't have to be long because it just jumps down to this routine. This routine then has the hard-coded address of this call, and then this call is going to jump to whatever was in the pointer. And here I'm doing a JML, so I'm doing a jump long, so there's no way to get back. But then when I call my OS and it's done, I'm going to do a return long, and it'll actually come back into this and then get me back up into this. And so you'll see that I can make multiple calls, get to the OS, and get back. And this little set of code down here is kind of a wrapper way to do that. What I was finding is if I try to directly do a JML, it will, or if a JSL, sorry, to a friendly name. Like if I said JSL to this system pointer, the assembler says, nope, I'm not having that because it's not seeing the third byte, the bank info. So again, if anybody's got any tips on how that typically is done, And again, I'm using Retro Assembler currently, but I was having the same challenge with the WDC assembler for the 816. And I'm sure it's just something I'm not understanding. As I was researching it, though, this was a common way that it was recommended to approach it, but just feels like it's a lot of jumping through hoops. Hopefully unnecessarily, there's a better way to do that. So these are just here to support the call to get me from my external flash at this higher addressing of 40 something all the way back down to the OS, let the OS do its work, and then get back out. So in this case, it's going to call this operating system. It's going to make the call to call OS. And then I'm going to say, well, go down to the system table, find the index of whichever command I want to run. And this was command 0, which was the print char. And then basically I want to jump to a routine that points to. So that's going to be this OS ILI print char, which I've placed into my OS file. And if I come down to that, it's just doing one simple thing. I took these other lines out temporarily, but it's just going to jump to my normal ILI print char. And when it's done with that, it's going to do a return long. So this is just a simple little wrapper to get me to some internal functionality in the OS and do a return long when it's done. Again, there's probably some significant improvements there and a more elegant way to do some of this, but let me show you the results. So now on my computer here, if I just press enter, and when I say computer, the 265, and I run app 1, you see it just says test now. So if I run that again, app1, and I get my TEST. So it's basically taking my keyboard input, I pressed enter, it says, oh, you want to run an operating system command. That command jumps me over to my program on the secondary flash. Secondary flash makes calls back to the OS to print four characters. So TEST as 4 separate calls. And then when that's all done, it gets me returned back and I'm back into my main OS in its normal loop. And I've kind of exited out of the application that I ran. And I can see that here, I'm back into my main OS and I can type things like help, and that's all working fine. That's what I have so far to start building up, and if I go back to this, what I've got supported so far is that I can, from my operating system routines, I know when you've pressed enter, I can check, did you run app 1? If you did, I go out and I jump to it, a long jump to that subroutine. It turns around and makes some calls back to the jump table call OS. And that call OS is making a sub call basically to then write out to my TFT LCD. And then it returns, it does the next character, it does that 4 times, and then at the end of that it returns back to whatever called it in the operating system, which then gets me back into my normal processing from the OS side. So that is the approach I'm going to take for a little while here, maybe permanently, maybe not, I don't know, but that jump table I should be able to support tens, hundreds, thousands of different routines that I can expose to applications. Applications just have to know what are the routine numbers and what are the parameters. That can all be documented. But then I could swap out the secondary flash with 10 other flashes. Each could have their own major application on it that leverages my OS and hardware. And as I mentioned, I do have a blog post started. It doesn't look like I have a web browser up. Let me just open one here quickly. I will be updating this post here that's just building an operating system, and not much here yet for content. I'm getting kind of started. What is an operating system? Well, maybe what's on my roadmap? What do I think I need to be working through? Maybe in a general order, and then some of the C app and some of the stuff I'm starting to do right now as far as this whole how I'm loading an app and dealing with that. But I'll keep building this out as I work through operating system work. So I think this is fun stuff. Maybe to some people this is not the thing they want to be doing, but I enjoy trying to figure out how to make a simple operating system, and just going to chunk my way through it. And so hopefully this wasn't too rambly as I went through this, but we'll see where the next video takes me as I'm on a journey for an OS for my 265.